would be nice. And chlorine is in the same period. It would be chlorine, it would get to chloride, would be octet. The octet for chloride would be argon configuration. And with this, you have sodium plus, and Cl minus is an ionic bond. Now let's do this with magnesium. Magnesium, in order to get the stable configuration, what would it do? It has how many valence electrons? 2. So it needs to kick off both of them, isn't that right? To get to neon configuration. And chlorine would take 1 to have an octet, but you would have to have 2 chlorines around there to make MgCl2. Okay? Now let's see if you understood. I have an element that forms a bromide that is 80% of bromine by mass. 80% of bromine by mass. So the element could be neon, potassium, or calcium. Here the atomic mass is here just for your orientation. So what is the element that forms a bromide bond with 80%, forms a bromide compound that is 80% bromide by mass? Why don't you think about this? You gotta give me everything I told you today. Actually, I just went through it. Make sure that's 80% by mass, by weight. Let's discuss this later, maybe. That's why you're learning. You gotta make a mistake first, or you get it right first. But you learn better if you learn from your own mistake. That way you remember. You can ask yourself the question, how many does neon have to kick out to have a stable configuration? How many does potassium to kick out to have a stable configuration? And how many does calcium to have to kick out to have a stable configuration? And then you make the compound. It has to be a ratio of 80% bromine by mass. Okay. You can wait till the cows come home. There needs to be some discussion. Remember, what was the example I gave you before? That one here, wasn't that? That one, how did that work? Okay. And so neon, I can tell you already. Neon is a noble gas. They don't react very well at all. In the old days, people thought they didn't react at all. And then one of my colleagues came along here in Berkeley, and he showed that you can make noble gas compounds. Okay? His name is Neil Bartlett. Unfortunately, he never got the Nobel Prize for it. He should have. Why don't we discuss this with each other and see if you come to a more unified answer? And maybe also to the right one. What is it? What would be the mass of B? What would be the mass of B? How much bromine would you have in there? What would be the mass? The mass is on the right side. It's not 80%, isn't it? 40 over 80. No, 120 over 80. No. What do you have? You guys discussing this? And? Getting it? Okay. Yes, you're getting there. You're getting there. Good. Of course, you have to give me everything you got here. Many of you have more, though. So neon is out. Neon already has a stable octet. It's a noble gas. I gave you that answer, and you know all this. So neon has 8. Potassium has 1. So potassium sheds that electron, and it becomes neon configuration. No, it becomes argon configuration. And with this, you have an octet. So it would have to give off 1 electron, and the electron would be taken up by the bromine. Is that right? So this one doesn't work. This one would be taken up by the bromine. Yes, you form an octet. They share this here. That would be positive. Not share. That would be positive. This would be negative. But now this is 40, and bromine is what is 80? Is 120 over 80. This is not 80%. Okay. So now the next one is calcium. Calcium would have to lose how many electrons? 2 to get to the argon configuration. And so, but bromine can only take 1 electron. So I need 2 bromines to take the electrons. And there's 1 here, there's 1 there. And this is how it works. And you now have a mass. This is calcium is 40 and bromine is 80. You have 2 of those. Calcium, bromine is 80, 160. 200 over 160. It's 100 over 80. Good. So now we come to the next form of binding. This is covalent binding, and this is electron sharing. And in this case, hydrogen does share the electron absolutely perfectly. There is no polarization. So hydrogen shares, they make an orbital, these orbitals overlap, they make a new orbital, a molecular orbital, we will learn about this, and so they share this and this, do it for this guy, do it for that guy, all right? They all are happy. So that would be a perfect covalent non-polar bond. Now if you have chlorine, the same thing, chlorine has 7, and this one has 7, so why don't we share? This one, they say, this has 2, 4, 6, 8, 2, 4, 6, 8, octal rule fulfilled, and with this you have Cl2. HCl, however, that does not share equally. So which one is more negative in HCl? The Cl, so that's negative, so there's delta minus would be there, so it's polar. And now I've thrown you a loop here, I make a dash here. The dash is always a dash is for 2 dots. Dot, dot equals dash, okay? Dot, dot equals dash. That's when you're too lazy, you could make a dash here, the dash here, the dash here. Then you know each dash is 2 electrons, okay? So now this one shares 1 with the chlorine, 1 it has by itself. So this is the duet, and this has 2, 4, 6, 8. That's the octet rule fulfilled, all right? We have a polar covalent bond. Now if you look at this, this is the potential energy diagram. This is the distance that these two nuclei have to, these two atoms have from each other. If you look at hydrogen, they're completely separated here. They look like this here. Now they are approaching each other, getting closer and closer. The electron clouds are seeing each other. They're touching each other, the orbitals. And when they are close enough together at the lowest possible possibility or condition and state, then they have formed this H2 molecule, which is the lowest energy state. And you see the energy state of each of them is higher before. And when they form that bond, they release 458 kilojoules per mole of energy. All right. If you go up here, then if you come too close, you get into the interaction again of the nuclei. And with this, you have a potential curve that goes like this. So you're getting this here. So it goes from a higher state to a lower state and releases energy. Can anybody tell me the number for the bonding energy or the bond energy? What's the bond energy? How many kilojoules per mole do you need in order to break that bond of hydrogen? 458 kilojoules per mole you have to put into that system to break that bond. So now you see, when you have water, So you have hydrogen and oxygen, that forms a duet, that forms an octet, that forms an octet. You need two waters for one oxygen, H2O, and this is the more electronegative, so this is delta minus, so that's polarized, and this is delta plus, and this is delta plus. So if I put this is how I do this is a dipole, that's how I usually show the dipole, it goes from plus to minus, and I have an arrow there in the direction of where the minus sign is. If I put this in an electric field, and I let it spin in the electric field, for example in the gas phase, and this would be the negative side, so the positive side, the hydrogens would orient themselves here, and the oxygen would orient itself there, okay? So that's what polarization is. Let's do a little bit of an experiment with water, and I have here, is that the picture I'm going to get? I gotta come back here. Okay. Front shot of me. Okay. So the camera's up there, obviously. Okay. Front shot of me. I have a piece of polyethylene, which is the better. Okay. There you go. So I have a piece of polyethylene or polypropylene, which is I can charge up by rubbing it with a piece of fur here. Okay. And rubbing it with a piece of fur, you know when your hair is statically, when it's very dry, your hair becomes static. So I'm charging up the surface here. And if I have a non-polar solvent, this would be hexone. That would be hexone. And I charge this up here. I hold it there. Nothing happens. See that? Nothing happens. I don't see anything. Okay. You tell me that you see this right. Okay. I'm not supposed to look at this. Okay. Nothing happens. Let me charge this up again. So where am I? You have this on picture? Okay. I charge this up here. Okay. And do it again. Hexane it says here. Nothing happens. Now what happens with water? Now let's do this with water. This way and this way. Okay. Okay, let's charge this up a little bit more. I got a little wet. Not so good. Let's see if we can bend the water. Now the fur is wet. Oh, that's no good. Okay. You see that? Okay, let's do this again. One time. Do you see? The water bends, doesn't it? Because it's polar. See that? See it bending? Okay, you got it? Everybody seen it? Nietzsche bends water. Okay? All right. So I showed you. Thank you, Karen. Thank you, camera, please. Alicia, thank you. I showed you that water is polarized. Okay, it's polar. It's like an electrical charged little dipole. And so HCl is also polar. See that? HCl gas does the same thing. If I put this in an electrical field, and I did an electrical field by just charging up the surface of the polypropylene stick there. So this would be delta plus, that's the hydrogen, and this would be delta minus. So if you go this one, this would be the duet rule, and this would be the octet here. You see, it has 8. Now, if you go a little bit more, octet rule. Carbon has how many valence electrons? 4. If you take hydrogens, you need 4, because each of them will furnish 1. So you have 1, 2, 3, 4, 5, 6, 7, 8. Octet rule fulfilled. 1, 2, duet 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 rule fulfilled. Ammonia has how many valence electrons? Just count it. It's S and P are the valence electrons. How many valence electrons does ammonia have? Ammonia. In nitrogen in ammonia, let's put it that way. How many valence electrons does nitrogen have? 5, exactly. 5 electrons. So you put nitrogen has 5 electrons, you would have a dot here, then 1, 2, 3. Okay? So when it makes ammonia, so it takes 3 hydrogen. It has 1 from the nitrogen, 1 from the hydrogen. Duet rule fulfilled here. 1 from the nitrogen, 1 from the hydrogen. Duet rule fulfilled here. 1 from the nitrogen, 1 from the hydrogen. Duet rule fulfilled here. And then I have a 3 electron pair. Okay? So I have 2, 3, 4, 5 electrons from the nitrogen. If I have nitrogen here, I have so we have 2 nitrogen. There's a perfectly covalent nitrogen here. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And if they share this, 2, 4, 6, 8. 2, 4, 6, 8. Okay? With this, the octet rule is fulfilled, and you have a perfectly covalent molecule. Now, if you have oxygen, the same thing. Oxygen wants to have 8, and each of them has 7. So 2, 4, 5, 6, 7. Okay? 2, 4, 6. Oxygen is what group? S6. Yeah, that's right. S6. Okay? 6. So they need to form a double bond. So that means 1, 2, 3, 4, 5, 6. Not an octet rule fulfilled, but if it shares it with the other one, you have 1, 2, 3, 4, 5, 6, 7, 8. For this one, and for this one, 1, 2, 3, 4, 5, 6, 7, 8. Octet rule fulfilled for both. Now you can do the same with carbon dioxide. Carbon has how many? 4, and oxygen has 6. So you can distribute it this way. Would it be polar or not polar? Polar would be polar, would have a dipole moment. There are exceptions, of course. Xenon hexafluoride. See, there is a noble gas. Xenon was a sensation when this was made in the 60s. Nobody believed it. Xenon hexafluoride has 2, 4, 6, 8, 10, 12. That's an expanded octet. So at times we can expand that octet. So the rule doesn't totally apply anymore, so we have to expand that octet. And if you have boron trifluoride, so boron has 1, 2, 3, 1, 2, 3, and the fluorine has 2, 4, 6, 7. So it has not enough electrons here. So we have 2, 4, 6, 8. 2, 4, 6, 8, but the boron has only 6 that it shares. So it's very sensitive to electrons because it's lacking electrons. If you put those together, ammonia and boron, so these 2 electrons will go right here, and you make ammonia boron trifluoride, for example. So let's do an experiment, and let's make salt, cooking salt. So we have sodium, and we need chlorine for this, doesn't it? And Karen will do it. Anyhow. We give up. And Karen will do this. And she has here, can we put the camera, can you direct this, please? She has a container here with chlorine gas. See that? That is yellow. Chlorine gas is yellow. And she is Karen, she has filled it with this gas. And now she has sodium, a little piece of sodium in the spoon there. And Karen heats up the sodium to get the activation energy going. And then she will insert that sodium into that container. And then let's see what happens. It's not going to be noisy, hopefully. So you ready? So the sodium has this nice yellow flame. You see that? That's the spectrum. That's how you can identify sodium. So now Needs a lot of incubation energy. You see, it's an exo and endothermic reaction. Exothermic reaction. You see that? We're making salt. The white, you see the white fumes? It's sodium chloride. And it will deposit eventually on the walls of the cylinder. So that's not how to make your cooking salt, okay? But this is the same compound, sodium chloride. All right, thank you very much, Karen. I'll see you on Wednesday. Karen, can you take a look at this?